Okay, so let me use my intro slide here to kind of present to you kind of the concepts of what we're going for. Um, the main overarching kind of like term we would give to this, they call it combinatorics, because it's all about how many combinations you can make of things. Here's an example. Let's say that I gave you four items. I don't care what the items are, but just imagine you have the numbers 1, 2, 3, and 4. And I asked you to take any two of them and put them in order. Here's how many ways you could do that. You could take 1 and 2. You could take 1 and 3. You could take 1 and 4, 2 and 3, 3 and 4, or 2 and 4. Those are the only combinations you have because everything else has already been accounted for. For example, let's say that you like just reached into a bag and randomly grabbed the number 3 and then randomly grabbed the number 1. Well, that's right here. It's been accounted for. Does that make sense? Or if you randomly picked number 4 and then number 2, that's been accounted for right here. And so there is no work to this. The answer would be there are 6 ways to do this. Does that make sense? And that's what a lot of kids either find frustrating or they love it, is that you don't have to do a whole bunch of writing down. You either look at it and you go, I get it, or you're going to hate it. Because then I'm just going to have to tell you what the answer is, and then you'll go, okay, I get it, and then try it again next time. So, so that's what I've got in my first slide here. Combinatorics is basically, it's all about probabilities and how to arrange objects. This is actually a really useful field in everyday life in the field of security. Okay? You guys all have a cell phone, right? Well, most of you have a cell phone at least, right? You probably have a password on your cell phone. Right? Now, if your friends tried to grab your cell phone and hack your password, let's say that your password was literally one button, and you had to guess from like say 1 to 9. It's not overly secure because your friend would try the number 1. Okay, Eric, try the number 2. All right, but like eventually they would crack your password if there was only one button to try, right? But like I don't know about you guys, I have a password which uses it's where you draw a picture. You guys do one of those like draw shape ones, right? Where in a way, what you've really got is 9 different little squares on there. And if I were to have just like tap one of them, that's pretty insecure, right? But if I draw a pattern that goes like and that uses a whole bunch of different characters, that makes it more secure. You get what I'm saying here? The password for your router would be another good example. Right? If the password for your router were only 2 digits long, eventually I'd guess it because I would go AA, AB, AC, AD, AE. You know what I'm saying here? And eventually I'd figure it out. But if your password was 19 characters long, well, then it can't be cracked as easily. Does that make sense? So when we're talking about stuff in this unit, a lot of it has to do with, well, what are the odds, what are the probabilities of you finding the correct arrangement? And we use this all the time in security these days. Okay. Here's another picture to try to reinforce the concept I've got here. Let's say that my daughter had 3 letters, 3 blocks, and I was using this picture here as the kickoff point. You guys ever see these little blocks? Kinsey has these. Okay. Let's say I gave her 3 of them, and I asked her to make a word out of it. You can actually make a word out of these letters. Can you guys pick out the one word in here?
Yeah.
Cab, yeah. But let's say my 5-year-old, who knows nothing about words yet, is just randomly flailing away trying to put letters in order. Well, here's kind of a picture of all of the ways that this could happen. She could go ABC, BAC, CBA, ACB, BCA, and then one of the 6 combinations actually spells a word. And so if I were to ask you what's the probability of her actually randomly spelling a word, you'd say it was 1 out of 6 because this one actually spells a word and the other 5 combinations are just gibberish. Does that make sense? That's what this unit is like. How much work was there to this? Yeah, there really isn't any. Okay, so the first thing I need to give to you guys is it's called a tree diagram. And a tree diagram is basically, it's writing out every single possibility that exists. And on this previous slide here, I literally wrote out all of the ways that you can rearrange the blocks ABC. And if it's on a small enough scale, you can literally write them all out. The problem is that once you get to a bigger and bigger scale, I'm not going to write out 10,000 possibilities. That's ridiculous. Does that make sense? So we have to have a little more logic behind how to solve these. Um, I thought this one was kind of fun. It's not actually a tree diagram, but it's a flow chart. You guys have seen something like this before, right? No. Anyways, this one's funny. Here's more of a mathematical version of the same thing. It's a flow chart for math. Okay. The scenario here is how many different ways could you flip a coin 3 different times. So I'm going to take a coin and I'm going to flip it heads or tails. And I'm going to flip it again, heads or tails. I'm going to flip it a third time, heads or tails. This tree diagram kind of shows you all the possibilities. Here's the first one. The first one could be heads. The second one could be heads. The third one could be heads. And so when you flipped your coin 3 times, all 3 times were heads. Is that possible? Is it likely? What's more likely is something like this. Heads, heads, then tails, which involves 2 heads and 1 tails. Now, that actually comes up again later in the scenario here. Like, take a look at this line right here. Here it goes tails, heads, heads. Tails, heads, heads. See how it has 1 tail and 2 heads there? That one's more likely. Another possibility is that it goes tails, tails, and heads, where you get 1 head and 2 tails. And then the last possibility is you could get just 3 tails there. This same kind of logic applies not just to something like flipping a coin, but say like when my wife and I, we have kids. I have 3 girls. What are the odds of me getting 3 girls rather than like say 1 boy and 2 girls or 3 boys and 1 girl? You guys kind of figure out the odds of someone getting 3 girls and 3 kids? Well, according to biology, depending on the time. I know because you guys are doing that there. The answer is 1 in 8. Okay? And I can show you that here. There are 1, 2, 3, 4, 5, 6, 7, 8 ways you can go through this tree. And for someone to have all girls, that would be like girl, girl, girl. There's 1 way in which all 3 of them are girls, and there's no boys. So right now, with where my family's currently at, there was a 1 in 8 chance of me having all girls. Does that make sense? If we have another kid, there's going to be a 1 in 2 chance that I have a girl the next time we have a kid, but like the odds of having 4 girls would actually be 1 in 16. Because really, the way this works is that the first time you have a kid, there's 2 possibilities. The second time you have a kid, there's 2 possibilities. The third time you have a kid, there's 2 possibilities. And when you multiply 2 by 2 by 2, there are 8 ways for that to exist. That's kind of what we're going to be doing in this section. Does that make sense? The math is basically just multiplying and adding or looking at a diagram. Okay, so let's try a really basic example. You guys ever go to the Marble Slab? You know this place? Okay. Imagine that you're going to a make-your-own ice cream place, and I'm going to limit the options here, though, because if we go with the unlimited options like they have there, it's too much. So let's scale it down. You have 2 choices, strawberry or chocolate ice cream, and then you can get 1 topping. So it can either be whipped cream, nuts, bananas, or sprinkles. Let's figure out how many ways you can make a sundae first by drawing this out. So if I were to draw it, it might look something like this. I could have either strawberry or chocolate ice cream. If I have a strawberry, it could have whipped cream, it could have nuts, it could have banana, or it could have sprinkles. Can you see how I'm doing this? This line right here means strawberry with whipped cream. This line means strawberry with nuts. This one means strawberry with banana. This one means strawberry with sprinkles. Well, this one right here, I said it's either strawberry or chocolate. But you ask good questions, because this would change if you could have plain ice cream. It would change if you could have nuts and sprinkles. And that's what kids hate about this unit is, pretty much for every question you ask, well, what if I did this? Well, then it changes the answer. But for right now, let's keep it simple. 1 choice of ice cream, 1 choice of topping. Okay, we can keep it basic. And there's another good point, because sometimes I give you a scenario where it's like, well, what if someone can't have whipped cream because they're lactose intolerant? And those are the little twists that you have to wrap your head around. Okay, stay with me here, guys. In order to finish off my tree diagram, I need to do the exact same thing for chocolate, though, because I could have had chocolate and whipped cream, chocolate nuts, chocolate banana, chocolate sprinkles. So my question is, how many different ways can this be done? 8. And hopefully you can visually see that there are 1, 2, 3, 4, 5, 6, 7, 8 pathways. Now, this works really well if you can literally draw them all out. But let's say you go to Marble Slab, and there's 19 flavors of ice cream, 14 toppings, 8 different kinds of cones, And you could say like have 2 scoops of ice cream or 1 scoop of ice cream. Or you could have 5 toppings or 2 toppings or no toppings, right? It gets confusing. So although once in a while we'll draw a tree diagram, most of the time we're not going to bother with the tree diagram. I got to show you some different logic. It's called the fundamental counting principle. Skip ahead to this slide here. We'll do that in a second. I'll do that one in a second. Skip to this slide first. Here's how the fundamental counting principle works. For each thing that you're going to try to do, however many ways it was possible to like arrange or pick those objects, you multiply. Okay. So I know this is kind of like weird math jargon here, but if like you could do something in P ways, something else in Q, and something else in R, the key is you multiply. I'd like to go back to the previous slide and show you on the chocolate ice cream one here how to get 8 a lot faster. There were, in this column right here, 2 ways to pick your ice cream. And in this column right here, there were 4 ways to choose your toppings. 2 times 4 is 8. Hey, you're looking for me, or did that make sense? Okay, let's try another one here. Rather than do a tree diagram on this, let's see whether we can use that logic to solve this problem here. You go to, say, like a restaurant, and it's got a really basic menu. Okay, so let's not have a huge menu. Let's pare it down.
Sydney Perry and Buddy Little Bear, please come to the office.
Okay, so you've got 4 choices of appies, 2 choices of entrees, and 3 choices for dessert. Let's assume that you can only have 1 each, and that you have to have 1. Does that make sense? Those are the rules. You have to pick from each column, but you can only pick once. So you can't have 2 desserts. Because if I give you the option of having 2 desserts, that totally changes the math. Well, the way this would work is you have 4 choices of appetizer, you have 2 choices of entree, you have 3 choices of dessert. You just multiply the numbers. 4 times 2 times 3 is 24. Yeah. Now, if I wanted to, I'm going to draw a really quick tree diagram here just to show you that that math still works out. But after this slide here, I'm never going to draw a tree diagram again because it takes too long. But just watch. I could have said there was appetizer A, B, C, and D. And then there's 2 entrees. I'll make those ones be like 1 and 2. Okay. So A, B, C, and D are my 4 appies. Then there were 2 entrees. And then for the 3 desserts, why don't I make each one of them be like X, Y, and Z? And this would be X, Y, and Z. Now, I'm not even going to keep writing this out. Stay with me, guys. Okay. There is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24 ways of making this work. Does that make sense? So, going back to where I started the class, some kids love this because they're like, wow, there's no work to this. All you literally had to do is multiply 3 numbers together. The problem is when we get to all these little twists, like, what if someone's allergic to something? What if you're allowed to choose 2 toppings? What if you're not? What if it's possible to not have dessert? How does that change things? Yeah, I know. Who would pick that? Okay. So what I like to do sometimes is talk about the subway problem, I like to call it. Now, back in the time where I made this slide, I stole this off of their website. If you guys can see right here, they used to advertise that they had over 2 million combinations on their menu. And that used to be like their advertising point, is that you could go to Subway every day for forever, and you would never have to get the same thing twice, because you could always pick something slightly different. Okay. What I find sometimes fun to do with kids here is let's actually figure out how many ways you could actually get something to eat at Subway. So, you're walking into Subway, you get in line. What is the first question they ask you? Well, be more specific. What kind of bread do you want? I think is the first thing they ask, right? Okay. So, first question. Well, let's get to that one in a second because those usually go together. How many kinds of bread do they have at Subway?
8? Oh, they have more now.
So for the sake of saving time here, can we estimate about 8, maybe 8 types of bread? Okay. So in the first spot here, what I do is I'd say for bread, I'd say there's 8 types of bread you can have. Okay. Then I think the next question they ask you is what size do you want? So you're talking either foot long or 6 inch. Do they give the 3 inch one still? Okay, so hypothetically, let's say that you could get a 3-inch sub. Then I guess the size. There are 3 sizes of sub you could buy. Okay, what's the next question they ask you? And when they say what kind of sub, usually the next thing they put on your sub is probably a meat, right? Okay, now, again, let's just assume that you're just getting one kind of meat, because I guess if you wanted to, you could ask them for like chicken and meatballs and bacon. So why don't we keep it simple? How many different kinds of meat do you think they could put on a sub, give or take? 10? 10 different kinds of meat, maybe? Why don't we go with 10?
Well, there's 3 for it. There's 4 on this side, but 8.
Let's go with 10 for right now to save time. What's the next question they ask you? Okay, how many kinds of cheese are there? Okay, now I want to introduce a new option though. Up until now, I think in order to have a sub, for the most part, you have to have bread, you have to choose a size, and you probably have to choose some sort of meat, although I guess you could have a vegetarian sub. You choose that one.
Yeah.
Okay, but bear with me here. Maybe there's the option of I don't want cheese. So you could have the 4 types of cheeses there are, and then there is a 5th option, not choosing cheese at all. Because that's going to come up next here. What's the next question they ask you?
Toasted.
Yeah. How many options are there for toasted? 2. There's 2 options. There is I want it toasted, or I don't want it toasted. Right? Okay, so let's keep this a little bit simpler though, because you're right. For every guys, stay with me, guys. Stay with me. I've got so much to teach you. Stay with me. There are so many little twists that you can add to questions that you guys can see that like this is going to get pretty big pretty fast. What's the next thing you put on your sub? Okay, now do you have to just choose one vegetable? Because you could choose all of the vegetables. You could choose lettuce, tomatoes, and cucumbers. So in a way, this is profound. This next step here. I know that there's say 12 vegetables there. Let's say there's 12 vegetables. Okay, but when we talk about veggies, we wouldn't put 12 here. Because what you're really being asked is this. Would you like tomatoes? Yes or no? Would you like cucumbers? Yes or no? Would you like lettuce? Yes or no? You're actually being asked, it's 2 to the 12. Good job. It's 2 to the 12. You're being asked a yes or no question 12 times. Make sense? I need to pause on that. This is a really important concept here. You're not being asked to choose one of 12 vegetables. You're being asked a yes or no question 12 times. Do you want lettuce? Yes or no? Do you want, you know what I'm saying here? Use that same logic now, because the next thing they ask you about is sauce. Sauce. How many sauces are in that little side container there? 8? Really? There's that many sauces? Yeah, but most of them are repeats though, right? Well, we'll get to that in a second. Okay, how about we go with this? How about we go with, say, 10 different types of sauce? But that same logic applies. You're being asked a yes or no question 10 times. Do you want mayo? Yes or no? Do you want light mayo? Yes or no? Do you want mustard? Yes or no?
Well, not really a word. Yeah.
This is getting big pretty fast here. Okay, and why don't we end here? Because that's the last thing. Salt and pepper. Let's end with that, okay? Because I know that you can buy chips or pop or cookies. Well, because you could get just salt, you could get just pepper, you could get salt and pepper, or none. So salt, pepper, salt and pepper, none. But hang on, this is actually easier to write like this. When it comes to salt and pepper, I have to go down here. Salt and pepper. Really, you're being asked a 2 to the 2 question. Because you're being asked yes or no to salt, and you're being asked yes or no to pepper. And in that 2 to the 2, it accounts for all 4 options, right? Yes, salt, yes, pepper, yes, both, no, nothing. So now let's grab a calculator, and let's see, just based on these rough calculations, how many ways can you get a Subway? 8 times 3 times 10 times 5 times 2 times 2 to the power of 12 times 2 to the power of 10 times 2 to the power of 2. Okay, you guys all know that the e to the power of 10 means that there's 10 decimal places after this. So this is actually like 4026 531 840. Okay, I need 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's that many combinations now. Yeah. Yeah. Now keep in mind, when I made this slide though, this was like years ago. I mean, they didn't have guacamole back then. They didn't have, I don't know, what other options they have, right? Yeah, now they add avocado. Now they add honey garlic. Now they add flatbread, right? So. Yeah, no, everybody gets hungry. And they also say we should take a field trip to Subway too. Yeah. Okay, so point I need to make here though. Would it be feasible to literally write out every single combination that you could get at Subway? No, please, that would never be possible. I think if you were to start writing them now, you might finish by the time you die. Like, it's that many, right? There's so many possibilities. This is the key to security, by the way. Because if there were 4 billion combinations and you asked somebody to try them all one at a time, they logically would never be able to finish going through every single one. Now, you could randomly get lucky on the second time you try it. You get what I'm saying here? But that's the whole point, is that if there are that many combinations and you had to try them all one at a time, that's what makes it secure. If you're a hacker, one of the basic ways that someone would hack something is using something called a brute force algorithm. Have you ever heard of this? Okay, what it literally does is it's a counter. It would go through 0, 0, 0, 0, then 0, 0, 0, 1, then 0, 0, 0, 2. And it would literally try every single combination from the 0, 1 all the way up to the however many there is. And it literally tries them one after another. Well, there's the question. It really depends on what other sorts of things they can use as code to kind of break into the system. Now, let's say take your iPhones, though. Does anybody have a setting on their iPhone where if someone tries to try it, like say, and they do it wrong 5 times in a row, it puts a timer on it, and then you can't try it again for 10 minutes? Right? I know that some iPhones, they even have a thing on it where if it's wrong 5 times in a row, it wipes the hard drive. Right? So there are some counters to this, but like brute force algorithms will work if there's not a backup in place. You just need enough time to just try every single combo. Okay, let's move on here because I got lots of stuff to do today. So now that we have a little bit of theory, this should be a lot faster to solve. You're going to flip a 2-sided coin, a 4-sided die, and a 3-sided spinner. How many different ways can you do all these tasks? 24. Yeah, 24. 2 times 4 times 3 is 24. This is what makes the unit, to some people, really easy because they're like, well, just do this. And to other people, as it gets more complicated, because, by the way, guys, we're like at this level of complicated right now, just so you know. It's going to get harder. But some people will just look at this and they'll be able to tell you the answer because they'll say, well, this is the answer. And other people will be like, I don't get why. So, anyways. But let's try a new example here. You guys ever play the game Scrabble? You have like different little tiles here. Imagine that you had 7 tiles. And just so that we can keep track of it, let's say that the 7 tiles were an E, an L, a G, an L, an I, those letters. Okay, English. Okay. Now, in Scrabble, once you have a tile and you use it, you can't use it again. Does that make sense? Because like once you use your L tile in the words you make, you don't have another L tile to use the next time. Okay, I get that. But you get what I'm saying here, though? Like, once you use your L tile, you don't have another one. Okay? But I want to point out how that makes sense in this question here. Because let's say that you had these letters at your disposal, but you could repeat letters. Let's say that somehow you were allowed to repeat letters. And I wanted you to make a 4-letter word. Okay? It doesn't actually have to be a word. But let's say that you tried to put 4 letters together in a row. Let me give you an example. I could use E, then L, then S, then H. I know that's not really a word, but I could try this combination. You get what I'm saying here? I know it's not really a word, but I could try it. Okay? How many different combinations could you make if you could repeat a letter? Well, here's how you'd solve it. you'd say for each of your 4 letters, I'd put a little blank here. How many choices do you have for your first letter? 7, yeah. Now, hypothetically, let's say that after you use your E, you could use it again for some reason. Well, the next time that you have to pick a letter, you still have 7 choices because you haven't reduced your choices by 1. The next time that you pick a letter, you still have 7 choices. And then the last time you pick a letter, you still have 7 choices. Now, by the way, I need to let you guys know, we're not actually going to solve what these numbers are. Okay? Don't bother on a lot of these examples finding what 7 times 7 times 7 times 7 is, because I'm going to assume you guys can handle that. In the interest of time, whatever that equals is the answer. Does that make sense? Here's my big point, though. A lot of times in everyday life scenarios, once you use something, though, you can't use it again. Like in Scrabble, once I use my letter L, I can't use it a second time. So if I want to make a word that has 2 L's in it, I can't do that. So here's how this would work if no letter can be repeated. I'm still going to need 4 lines. The first letter, I have 7 choices. The next one's going to be 6, because whatever I picked for my first letter is now out of the running. There's only 6 choices left. The next is going to be 5, because whatever I picked for the first 2, both of those have now been used. And then 4. How many letters are left over? 3, I think, right? Right? I'm stopping at 4 because of the 7 letters that I had, I picked 4 of them. 3 of them, I guess, aren't being used. Do you see how this changes the math a little bit, though? Here, if I can repeat letters, it's different than if once you use it, it's out. Well, one of my jobs now is to help prepare you for any sort of little twists and tricks along the way. Because, Jake, you pointed out that when you play Scrabble, sometimes you have to have that letter go in a certain spot because that's to match up with the one that's on the board, right? So what if I give you this parameters? First of all, you can't repeat letters because Scrabble doesn't work that way. And you have to start with the letter E. Now there's a new twist. Well, you're still making a 4-letter word. How many choices do you have for the first letter? Yeah, because it has to be E, right? How many do you have for the second letter? 6. Because it used to be 7, but E is now used, so then it's 6 times 5 times 4. Do you see how pretty much any, if you can dream up the question, we can answer it. You can say, well, what if this? Well, yeah, does that make sense? And that's what makes this unit so big. It's so simple. You are literally multiplying numbers. Once in a while, you add them. It's so simple. And yet, it's all about context. You have to figure out whether or not you can repeat numbers or not. First and last letters have to be a vowel, and you still can't repeat a letter. So this letter here has to be a vowel. This letter has to be a vowel. These ones right here can be anything. So let's walk through when you make the word here. How many vowels do we have in the letters? We have 2. Okay. So let's say you start with this one right up here. You have 2 choices of vowels, right? Well, you know what? I should probably go to the end of the word and end with a vowel right away first to figure out what I have left to work with, right? If I've used one of my vowels right here, how many vowels do I have left to go here? Just 1. Okay, well then in the middle, there's really no restrictions. Well, how many choices do I have left, though? 5 for this one, and then 4. Now, some kids might ask, well, what if I didn't want to make my word in that order? Well, what happens if I were to change this up a little bit? What if I were to have started with the last letter? So, like, I'll start with the last letter, use my vowel there, and then I'll put my other vowel here. And then, let's say I want to use my 5 tiles here, my 5 tiles. Does it really matter what order it goes in when you multiply? Yeah, it doesn't really matter. So, again, I don't actually care what this number equals. Okay. On your assignments and on your tests, by the way, please do tell me what it equals. But while I'm doing notes to save time, can we leave it there? Cool. Okay. For any of you guys who are sports fans, you guys have heard of March Madness? You guys know, like, who knows what a bracket is for March Madness? Anyone done these before? Okay. So for those of you who haven't done one before, basically the idea is that for every single one of the games that's going to occur, you're supposed to pick a winner. And most March Madness pools, they give points based on how many games you get right, and then they give a winner. Every year, a guy named Warren Buffett, ever heard his name before? He's like a super rich billionaire. He's offered a $1 billion cash prize to anyone who has a perfect bracket, a $1 billion cash prize to anyone with a perfect bracket. By that he means you have to guess every single game right. I'm not just saying that you have to get most of the games right. Every single game you have to get the winner. Does that make sense? So if in the first round you pick Duke and Duke loses and you get everybody else right, it doesn't matter. You don't win.
You get anything?
No. So now think about this. Some people would be like, $1 billion, how can he do that? I want to talk about the odds of this happening. Okay. Now, hypothetically, even if you were the world's greatest gambler and you had like some sort of great insight here, let's just, for the sake of argument, just say that your odds are roughly 50-50 of getting it right. Does that make sense? What it really means is that for this first game right here, you had two choices. You could either have picked Kansas or whatever the heck that is. And on this line right here, you had two choices. You could have picked either one of those teams. You know what I'm saying here? Every single one of these lines, you had two choices that you had to make. Now, the way it works is that in March Madness, I believe there are 63 games total, if you add up all these lines on here, which means that you are being asked to make a choice of either Team A or Team B 63 times. 2 to the power of 63 is 9e18. There is one perfect bracket that can be made, though, right? The odds of somebody having a perfect bracket are 1 in that number there. I don't even know how big that number is because it's beyond the scope of like millions, billions, trillions. It's way beyond that. Warren Buffett's never going to pay out this prize. You know what I'm saying here? It's just not going to happen. The only way it would happen is if I had time enough to fill out like a billion brackets and literally write out every single one, then one of them would have won. But like, do you think you'd have enough time in your life to actually write them all out?
Well, yeah,
As a
good
school,
class
everybody,
together.
yeah, as the school spread the billion.
Right.
Still get a couple million.
Okay.
Yeah.
Here's another place that we can talk about counting principles. I love this unit. This is one of my favorite units because I can show you where it's applicable to real life. Not that I expect everybody here to do this in real life, but hopefully you can appreciate that this kind of math, it occurs in life. Gambling. Gambling is all about math probabilities. If you guys have seen any sort of gambling movies like that Blackjack movie with Kevin Spacey, what was it, 21? Have you seen that one? Like, math is all about, gambling is all about math. Right? It really is. We can do the same sort of thing here. Math is all about gambling. Okay, so first off, are you guys all familiar with a regular deck of cards? Is this something you've seen at some point in your life? Now, okay, quick disclaimer, by the way. I'm not advocating gambling, okay? Okay? I'm not suggesting you should all be gamblers, but it's a great way of showing you how this works. So here's a deck of cards. Here's my question. Let's say you were playing a game of poker, and you, in order to win your game of poker, you needed to either get a black face card or an ace. Say that one more time. You're playing poker, and the only way you're going to win is if you get either a black face card or an ace. Those are the only ways that'll make you win. Everything else you lose. What are the chances of you winning? Well, let's start looking at them. How many black face cards are on here? Yeah, there's these guys right here. These are the black face cards. But you can also win with an ace. So 4. So now, what some people might do is they might say, oh, okay, well, there's 6 right here. There's 4 right here. 6 times 4 means there's 24 ways we win. That's wrong. It's all about one small word. The word right here is or. Whenever you have a scenario where you have to win with this or this, it's not multiply, it's add. If you had to win with this and this, multiply. But if it's one option or the other option, don't multiply, you add. There's 6 cards here you could win with. There's 4 cards here you win with. You have 10 ways you could win. What gamblers then do is they then weigh those odds and they say, okay, I got a 10 in 52 shot of winning. And then they try to figure out, well, is it worth it for them to gamble? Does that make sense? Does that make sense to you guys? Okay, let's try another example here. Let's say that you win on any red card or a 10. you went on any red card or a 10, which really isn't poker, but how many red cards are there? Well, half of the deck is red, right? If you know this. So there are 26 cards right here that are red. Guys, stay with me. You're way too distracted today. There's 26 cards here that are red. And then in this column right here, here's all the 10s. So there's 4 10s. But the answer is not 30. Yeah. So one of the things you have to consider, and this is again those little twists and tricks, is there are some red cards that are also 10s. We can't count them twice. Does that make sense? So although there's 4 10s and 26, the answer here is actually 28 because I can't count those guys twice. Does that make sense? So these are the things that I'm going to show you as many examples as I can, but it's one of those things where it really can't be taught in the same way. Like either you get it and you go, oh, I caught that trick, or you'll miss it. And okay, that's actually what this next slide here is about. The word I'm going to use there, it's something called mutually exclusive. Mutually exclusive basically means that there's no overlap. Okay, like right here, let's say I want you to draw an ace or a king. Do I have to worry about somehow drawing a card that is both an ace and a king at once? No, those would be mutually exclusive. It's either in this category or it's in this category. I don't have to worry about doubling up. But if I tell you to draw an ace or a club, that's not mutually exclusive because there is one card that is both an ace and a club. We call it the ace of clubs, right? So you always have to be careful that sometimes something might be in both categories. We often use a Venn diagram for these. If these were aces and these were clubs, there would be one card in the middle, which is the ace of clubs. And because of that, the second one is not exclusive. Wait, here is some, how do I describe this? Notation that if you're in -2, they put on your test. -1, for some reason, it's not on yours. So, sorry. So in -2, I want to explain to you guys some notation here. If multiple things need to occur, you need to do and. And means multiply. And one of the symbols that you might see is this thing right here. This symbol right here means, which one is it again? This one is the intersection. And this is where both have to occur. So if both things have to occur, you multiply. The way this notation basically works is the little n stands for the number of ways that something can happen. If you want to figure out the number of ways that A and B happen, you take the number of ways that A happens and you multiply by the number of ways that B happens. Okay. But if there's option, you need one or the other. That's this symbol right here, which is like a U. This is known as union. And this is where only one has to occur. Okay. This one here, they both have to happen, multiply. This one here, if only one has to happen, add. Okay. Now, both curriculums, you have to understand the concept, but the only one where they actually use this notation is -2. So if you ever see this symbol right here, it really means to multiply. If you ever see this symbol right here, it means to add. Does that make sense? Okay, let's try another example here. So you have a telephone number in Fort Macleod. If you have a home number, it probably starts with 553, right? That's the general prefix for here. Let's say that Fort Macleod starts to get so big that over time, they start to run out of phone numbers. And so what I want to do in this example here is figure out how many different phone numbers are possible. Okay? So here's the scenario. Telephone numbers in an area consist of either the digits 553 followed by any 4 digits, or the digit 6 followed by either 3 up to 8, and then the remaining digits can be anything. My question is, how many telephone numbers are available? Well, a lot isn't going to cut it, though. So, let me see if I can help explain this one to you. If the first number has to be a 5, when you start typing in your number on the phone, how many choices do you have if it has to be a 5? One choice. I'm not even going to write the 1 then, if that's okay. The second 5, you also don't have a choice for. The third 5, you don't have a choice for. So really, all of this, you don't have any choice. But then for the next digit, how many choices are there? 10. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So if Kinsey were to grab the phone, type in 553, and then randomly just pick other numbers, there's 10 choices for what she could pick here. There's 10 choices for what you could pick here. 10 here and 10 here. But all of these right here, you didn't have a choice. How many phone numbers were available in Fort Macleod then if it was only 553 as your prefix? 10 times 10 times 10 times 10. There's actually 10,000 phone numbers available in Fort Macleod. Now, normally that wouldn't be a big deal, except now start thinking about this. If all of the businesses, though, needed a phone number too, and our school, say, has, like, say, 4 phone lines, and the hospital has 80 phone lines, you get what I'm saying? Those get eaten up pretty quickly. And eventually, maybe a city then needs to open up a new set of numbers. So now the new numbers, yeah, then you just change it slightly, right? So what's happened, I'm guessing, is that eventually all the phone numbers got used up, and they had to start making new ones. Does that make sense? So my scenario here now, stay with me, guys. If it has to start with a 6, how many choices do you have? Okay. This is a tough question, this next one here. If the next digit has to be between 3 and 8, how many choices are there? 6. Count them. 3, 4, 5, 6, 7, 8. Because you have to include the 3 and the 8 on both sides. So it's not as simple as just going 8 minus 3 gives 5. So there's actually 6 ways you could do this number here. And then after that, if we don't care, then there's 10 choices for everything. Now I want to pause for a second here. When you are using Scrabble tiles, once you use a tile, can you use it again? When you're typing phone numbers into your phone, if I use the number 7 in somebody's phone number, does that mean I can't use a 7 ever again? This is the single hardest thing you guys are going to come across in this unit, is you have to figure out whether or not it's logical to reuse a number or not. Because otherwise it would have gone 10 times 9 times 8 times 7, but in this example here, it's 10 times 10 times 10 times 10. It's actually 6 times 10. So I believe if you put these all together, it's actually now 600,000. But that's not my final answer. My question now is, how many total phone numbers does Fort Macleod have? What should I do with these two numbers here? Add. Because of this one word right here. You can either do a 553 type of number, or you can do the alternate phone number. But you can't do both, right? I can't do a 553 number and also type in the 638 number. So because it's an or, the final answer to this would have been 610,000. Because you have to add these to each other. Does that make sense? Okay. License plates. Another good example of these. Everyone has to have their own unique license plate. So let's say that in a certain place, you need to have these rules here. The first rule, though, is that you can't have a letter that is either I or O. Let me think of why you might not use I's and O's on a license plate. And they look like ones and zeros, right? So this would be a good example of a question where I'm going to give you like a little twist to it. You can't use every letter in the alphabet. You can only use all of them except. So how many letters are in the alphabet? 26. But if I and O are out, there's 24 possible letters you can use. So I'm going to start kind of writing out the basic structure of this here. It consists of any letter other than I and O. So there's 24 possibilities here. Then it's followed by 3 digits, the first of which cannot be 0. So if this can be any digit, how many digits are there? Actually, normally there are 10, but if we're not using 0, then there's 9. Now, can I use 0 here, though? Yeah, because only the first one couldn't be 0. Now, on a license plate, once you use a digit, can you use it again? There's no reason why I can't have a license plate that has like 2 5s next to each other. So we're back up to 10 again. and then we're back up to 10 again, right? These were all of your numbers here, but this was the one restriction. You couldn't have the 0 here, but you could here and here. And then it says it's followed by any 2 letters, but for whatever reason in this scenario here, they can't be repeated. So, how many letters are left though? Well, but hang on a sec. It says just the first one here couldn't be an I or a 0, I believe. Does that make sense? So I think back here, maybe we can use I and 0 again. So if that's the case, then you had 26 possibilities here. But then if you can't repeat it, then it's 25. But this is a really good question here is you'd have to ask, well, can I use I and 0 here? Because if I can't use I and 0, then it actually would have been 24 and 23. Does that make sense? So the way I'm interpreting this, though, it just said that the first letter can't be I or 0. It said any 2 letters for these last ones here. So it looks like I and 0 are back in as possibilities here. Those little twists are what you have to wrap your head around. Can you guys kind of appreciate how, I don't want you need to feel sorry for me in my job, but like how it's challenging for me to prep you for this because there's a million little twists that could occur and I have no idea what they're going to test you on. So I'm going to do my best to get you ready for as much as I can think of. Oh, and then on the diploma, whatever twist they give you, hopefully at the time you'll look at it and go, we did one like this, and you'll be like, I know how to solve this little puzzle, because this is like solving a puzzle. Okay, new scenario. You're an employer, and you have 9 employees, and you have 9 ski hills, and you need to send each employee to a ski hill. How many ways can you send your 9 employees off to your ski hills? So I'm going to show you a couple of possibilities. Should it be 9 times 9 times 9 times 9, something like that? Why wouldn't that be fair? Yeah, once you send the employee away, you don't still have 9 employees. That employee is now gone to the ski hill. Does that make sense? So it's probably more appropriate to say something like this. The first time you look at your employees, you say, I've got 9 people. Okay, you go to the first ski hill. You had 9 choices. Well, now you've sent one of them away. Well, now there's only 8 people left. And then eventually, it's going to look like this. 7, 6, 5, 4, 3, 2. Now, I want to talk about the end here. So imagine that you guys are here, you're my employees. You go to the first ski hill, you go, you go, you go, you go. And I get down to my last 2 employees. I'll use you 2 because you're over there. Luna, go to that ski hill there. How many choices do I have for the last ski hill? Well, I just have Joselle in front of me. Does she actually even have a choice? No. Which is why the last blank is often a 1, not a 0. We have 1 choice. Okay? Now, I know it's like you don't have a choice, but not having a choice is actually your 1 choice. So what Jordy was just describing there is the point I want to make. Guys, never multiply by 0. Because what happens if you take this whole string of things and times by 0? Then it's 0. Okay. So even when it seems like you don't have a choice, the 1 choice you have is still a choice in this. Does that make sense? Okay, now I want to change this here. Let's say you had 11 employees, and you had the exact same scenario here. Well, then you had 11 people who could go to the first ski hill. 10, 9, 8, 7, 6, 5, 4, 3. Why am I stopping at 3? I ran out of ski hills, yeah, right? So I only had 9 ski hills. Here's the first, second, third, fourth, fifth, sixth, seventh, eighth, ninth ski hills. How many choices did I have at my last time, though? I actually had 3 choices. Because really, I had 3 people left here, and I sent one of them away, and then the remaining 2, I guess, aren't going to work today, or whatever happens to them. Does that make sense? Yeah, they're on break. They're working the lodge. Here's the point I need to make. This scenario comes up a lot, where once you select somebody, you have to go to the next number down, and the next number down, and the next number down. And it comes up so often that mathematicians have devised a new, what's the right word to use? A new character, a new letter, for lack of a better word, to describe this scenario. It's on my next slide here. It's called a factorial. And the letter we use, not a letter, the character we use is an exclamation mark. which is kind of cool. If you ever see an exclamation mark, this is what it means. If you ever see 9 exclamation mark, it means 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. If you ever see 5 exclamation mark, it doesn't mean that like 5. It doesn't mean you're shouting. Okay? It would. The exclamation mark basically means take that number and multiply by every number lower than it until you get to 1. Let's talk about 2 things about this. First of all, why do we have to stop at 1? Yeah, 0 wouldn't make sense because as soon as you multiply by 0, the whole thing's nothing. Second thing, can I do 5.2 exclamation mark? When we're talking about objects, you either have an entire object or no object at all, right? You can't have 5.2 of something in this scenario, okay? These have to be whole numbers. So on your graphing calculators, or any calculator, there should be a button on here somewhere that's an exclamation mark. Let me show you where it is on this one. First, you'd have to type in, like say the 9. Then go to math. Now, there's math, there's numbers. I don't know what CPX stands for, but this one right here, PRB, is probability. Probability.
I'm gonna forget that.
And if you go down to number 4, it's 9 exclamation mark. This will tell you what 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 is. Yeah. Sometimes if you pick too big of a number, did you get overflow?
Yeah.
It means that your calculator went past the power of 100 and it just gave up because the number was too big.
Oh dang! I did 9 exclamation point to answer that exclamation point.
Ah. Yeah, because it's getting too big now, basically. Okay, can I go back a slide here, please? I want to show you a quick way of writing both of these numbers now. Rather than writing this out, a shorthand way of writing this first one would be 9 factorial. However, the second one is not 11 factorial, because for it to be a true factorial, it has to go all the way down to the number 1. And this one here stopped at 3. So let me show you the quick way of writing this one. This is 11 factorial divided by 2 factorial. Okay, take a second to ponder why it's that, and then I'll talk about it. But I want you guys to think about it first. Why would that be appropriate for this? 11 factorial literally means 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. But do we want the 2 and the 1? We don't want the 2 and the 1. So if I divide by 2 factorial, it'll cancel off the 2 and the 1 that you don't want. A really clever way of thinking about this is that this number on top here is how many total employees you have, and the bottom number is the people who didn't get a job for the day. You had 11 employees, 2 of them didn't get to go to work. Make sense? You guys aren't giving me your best attention today. Okay, let's try another task here. If I were to ask you to solve for 10 factorial over 7 factorial, I don't actually want what the number is. That's not my point right now. It's equivalent to this. 10 times 9 times 8. Does that make sense? 10 factorial over 7 factorial is 10, 9, 8. Because the 7, 6, 5, 4, 3, 2, 1 all canceled out. Does that make sense? Now, it is possible to have multiple factorials running at once, like say in this one right here. What this one really means is 37 times 36 times 35 times 34. And I'm not going to write the rest of them, because can you guys see how this 33 right here kind of gets rid of the rest of them? However, I still need to, on the bottom, have a 4, a 3, a 2, a 1. I don't actually care what it equals. I'm assuming you guys can use a calculator. Okay? The point I want to make is that this is what this actually means. If you're in dash 1, they definitely will ask you something like this. If they're in dash 2, maybe. I don't think I've seen a lot of questions on this, but they might then throw letters at you like you guys love. Okay. Let me show you how to solve this one here then. What does n factorial then really mean? Watch this. N factorial means take n, multiply by one number lower than it, multiply by 2 numbers lower, multiply by 3 numbers lower, and keep doing that until eventually you get to the number 1. That's what n factorial really Make sense? N factorial means for some unknown number, start with that number, multiply by 1 less than that number, multiply by 2 less than that number, and just keep going until you run out of numbers to work with. Well, we're not actually solving for n, we're just seeing what it's equivalent to. This isn't about solving, this is about simplifying. What cancels? The n and the n minus 1 cancels. Here's the correct answer then. N minus 2 factorial. Because n minus 2 factorial means start with this number here and keep it going until you run out of numbers. Isn't that kind of weird? Yeah, that's the right word. Interesting. Okay. If you're in Dash 2, I want to show you it, but I don't think I've ever seen them test on this. Yeah. Let's try this one here. What does n plus 2 factorial mean? Well, it means start with n plus 2, whatever the heck that number is. I don't even know what it is. Well, what's the next number after n plus 2 going down? N plus 1. Then n plus 0, I guess. Then n minus 1, then n minus 2. And you'd keep doing that for forever. Okay, now for the bottom of the fraction. What does n factorial mean? Start with n. Then do n minus 1, then do n minus 2, and just keep doing that for forever. What cancels? This and this would cancel. This and this would cancel. This and this would cancel. And the doing it forever, I guess, would cancel. So what are you left with? That's what you're left with. Well, this was n plus 0 right here. Isn't n plus 0 really just n by itself? Does that make sense? Sorry, I glossed that step right here. The n plus 0 really is n. Okay, how much more do I got here? I got so much more. Are you guys about done for right now? Could I call it quits? Okay. Because pretty much, just so you guys know, I'm just going to start teaching all 3 of these lessons just in sequence. So if we're at a point where you guys are mentally done, why don't we call it a day? So tomorrow, let's pick this up, and then we'll move right into the next set of notes. And then Monday, we'll do the same thing. Sound good? So, okay. One last thought. You guys should probably start looking at your assignment, though, just little by little. You won't be able to do every single question because I may not have taught you how to do those tricks, but at least start looking at them. Sound good? Okay. Let's call her a day.